Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back to another session. And this one we're talking about applying Newton's laws, and that's a follow through from 5.1, which talks about the three laws of motion by Newton. Just a quick revision on that. So the three laws are the law of inertia, which basically just says that things don't like changing what they're doing. So the more mass an object has, the more inertia it has, which means just the more laziness it's got, the more it doesn't want to change what it's doing. If it's sitting still, it wants to stay still. If it's moving, it wants to continue moving. That's what that law is about, basically. And then we've got the law that states that force is related to, or is equal to, mass multiplied by acceleration. So we've got force equals ma. That's the second law. And then we've got the third law, which is for every action there is an equal and opposite reaction. They have to be both equal and opposite. And we're going to be utilizing these laws today as we apply them to different scenarios in physics. And inshallah, you will all understand it. Okay, let's go. So the name of this, well, we're just going to say answers and notes. Okay. Let's have a look. So let's begin by talking about free body diagrams. And what are free body diagrams? Well, it's just a way of showing us the forces acting on an object. That's all it is. So let's say, for example, over here, we've got a satellite in outer space. We've got a satellite in outer space. And this satellite is being pushed by two different astronauts. One is pushing up while the other one is pushing to the right, as can be seen. Now, the free body diagram doesn't include the actual image of the astronauts. It just has the object with forces acting on it. And it's a very important skill to have because it helps you visualize what's going on. Okay, it helps you visualize what's going on. So what we have over here in this example is two astronauts, and they are pushing on a satellite in outer space. And one is pushing with 46 newtons to the right, and the other one is pushing with 46 newtons upwards. That's easy enough. And we are being asked, what are we being asked? What are we being asked? Read the question carefully, and let me change the color. What are the magnitude and direction of the satellite's acceleration? Now, it's common sense if you were to visualize this. If one astronaut is pushing upwards this way, while the other one is pushing this way, then obviously this satellite is going to be moving somewhere, and it's going to be moving that way, isn't it? Because we've got two different forces acting from two different directions. That makes sense. So what we have here is the body diagram, the free body diagram. And what we can do is we can use that to work out the overall force, because essentially speaking, we can actually form a triangle using these forces. So this is F1, this is F2. And let's look at the values. So 46 and 46. So it is an equilateral as well as a right angle triangle. So it's an equilateral right angle triangle. These two are the same as well as 90 degrees. So we've got the hypotenuse, and the hypotenuse is going to represent the overall force. And the overall force is going to be, simply speaking, using Pythagoras theorem, is going to be, assuming that's A and that's B and that's C, is going to be A squared equals B squared plus C squared, and the square root of, so A is going to be the square root of B squared plus C squared. So let's work it out. Let's work it out. 46 squared plus 46 squared, and the square root of both those. So that's going to give me 65 newtons. Now that's not the answer yet. That's just the force. And it's asking for the acceleration. How do I get the acceleration? I've got the force, I've got the force. Now, don't be confused by the A, that's just a variable. But I've got the force is equal to 65 newtons, because remember, these are forces here. Now, let's have a look. So, force equals mass times acceleration. And so, what I need to do now is put 65 equals the mass. Am I given the mass? Yes, I am. It's over here, 940 kilograms. 940 multiplied by the acceleration. So let's find out how fast this satellite is moving. It's going to be moving 65 divided by 940, which is equal to 0.69, no, sorry, 0.069 meters per second squared. Remember the unit for acceleration, please. Okay, and that's how you do that. Easy. So what we needed to do first was find the forces acting on the satellite. Then we find the overall force, which obviously is the hypotenuse in this case. And then once we found that force, we could use Newton's second law, force equals mass times acceleration, in order to find the acceleration. Easy. Right, let's go to the next slide. Here we have a question that says, suppose the force exerted by the astronaut 1 in figure 5.7 is increased to 58 newtons as opposed to 46 newtons. If everything else in the system remains the same, what are the magnitude and direction of the satellite's acceleration? Let's have a look. Initially, that satellite, remember, had 46 and 46 acting in both directions. That's astronaut 1, that's force 1. So this time he's saying that astronaut 1 now is changing. He's pushing a bit more. So he's putting in a bit more force. So this time it's 58 newtons on this side, while still 46 newtons on this side. Is it 46? Was it 46? Let's see if you're paying attention. 46 indeed. 46 newtons. So now I need to work out the overall force, and this time it's going to be at a different angle too. So let's work out the overall force. It's still the same formula, guys. So the overall force is going to equal the square root of 46 squared plus 58 squared. And that's going to equal 46 squared plus 58 squared. And that's going to equal 74 newtons. Now, it's not asking me for the force. What is it asking me for? Remember to read the question. It's asking for the acceleration. Force equals mass times acceleration. I've got 74. Remember, this satellite has a mass, what was it, 940? 940. Quite a heavy satellite. 940 kilograms multiplied by the acceleration. I'm going to move this to the left-hand side, and that's going to equal A. So 74 divided by 940. This time the acceleration is equal to, for those of you that have worked it out, you can check your answer with me, 0.079. Okay, are we working with two significant figures? Yes, we are. Meters per second squared. And that is the answer. Okay? That's the answer to that one. So the first step was to find the overall force. The second step was to use F equals ma. Simple as that. I always like to draw the diagram though, it just helps me visualize things. Are we done? No, we're not, because it's asking for the direction as well. So this is where the diagram comes in handy. So it's looking for the direction, so it's looking for the angle. We know it's northeast, but we need to know the angle. So it's going to be what? This is the opposite, and this is the adjacent. This is the hypotenuse over here. You could use any of them, but I've got the opposite and the adjacent in the diagram. So I'm just going to go 46 divided by 58, and then TOA, SOHCAHTOA, remember that. So, TOA. You couldn't do physics without maths. They are just in love, physics and maths. You can't separate those two. So 46 divided by 58, we get a number, and then shift 10, and that's going to be 38 degrees. So it is, the answer is 0.079 meters per second squared at 38 degrees north of east above the x-axis. Fantastic. Let's move on. Oh, here we go. So here's a quick revision of something you probably would have encountered in grade 8. So it talks about weight and mass. So obviously mass is the amount of matter inside your body. Mass doesn't change, well, unless you diet and exercise. But mass isn't going to change if you simply go into outer space. If you go to the moon, you'll feel lighter because the weight is less. The pull of gravity on you is less. The same way, if you go into outer space, you'll feel weightless, which means you just float around. Your mass hasn't changed. You still have the same number of atoms, essentially, except you now have a different pull on you because you're no longer on Earth, and therefore gravity isn't working on pulling you, and so therefore your weight has changed. So what is the relationship between weight and mass? Obviously, it has to do with gravity. Well, yes, it does. Here we have the relationship. So remember that force equals mass times acceleration. Force equals mass times acceleration. Also, for those of you that like triangles, I like triangles. I'm not gonna lie, I like triangles. So if force equals mass times acceleration, well, remember weight is a force. Gravity causes weight. So gravity is not a force in itself, but you'll see it being referred to as gravitational force. Gravity causes weight, um, which is a tricky one. Weight is the force. So weight equals mass times acceleration because weight is a force. So that's just a way of writing it. So rather than writing force again, we just write weight, or you could write force, weight. The force of weight, that's what that means, FW. But weight equals mass times acceleration. What's the acceleration? Here on Earth, it's gravity, so it's G. That's that's acceleration, and that is just a force. They're exactly the same, just different letters. So weight equals mass times gravitational acceleration. Okay, moving on. So just back here for a second. So let's say, for example, I have a mass of 85 kilos. Here on Earth, my weight is going to be 85 kilograms multiplied by 9.81. 9.8 is sufficient. And that's going to give me my weight in newtons. Okay, so 85 times 9.8, and that's going to be approximately 833 newtons. Easy peasy, lemon squeezy. Okay, right. And if you're wondering what the unit of G is, it's acceleration towards gravity. Okay. Let's have a look here. Here we have an example of a firefighter who's going down this hole, and what are we being asked? We're being told the fire alarm goes off, and the 97 kilogram firefighter slides down the pole with a constant acceleration of 4.2 meters per second squared. What is the upward force, F, exerted by the pole on the firefighter? Let me just sort of simplify this by rewording this last sentence here. What is the upward force, F? I'm just going to highlight that. Yeah. This part here needs to be understood before we can even start doing the work. That is essentially the most important part of the question to understand it. I mean, it's pretty obvious, isn't it? You need to understand the question to be able to answer it. It's surprising the number of students who don't get that. Okay, so what do? We read it again. What is the upward force acting exerted by the pole on the firefighter? What this is saying is what is the amount of force that the pole is holding? Imagine a situation where the pole is like that and there's a deck on top, and the firefighter is essentially standing on it. And if I ask you, what is the amount of force, what is the upward force exerted by the pole on the firefighter this time? What I'm saying is, what is the amount of force that the pole is carrying? What is the amount of force that the pole is withstanding? How much is the pole taking? The pole is taking the whole weight. The weight of the firefighter is 97 kilograms multiplied by 9.81, which is 950 newtons down. Well, guess what? The pole is carrying the whole weight. It's pushing up with the same force, so it's 950 newtons up. That's not the situation here, though. The situation here is that the firefighter is sliding down the pole, and the pole isn't pushing up with 950 newtons, because if it was, then the firefighter wouldn't be moving. Except it's taking some of the weight, but it's not taking the whole weight. And no, they're not telling us the force it's carrying, but they are telling us the acceleration. So they're saying, you know what? He's accelerating down with a force of 4.2. Had he been falling, had the firefighter just fallen off the hole, had there not been a pole and just the hole, and the firefighter just fell through, what would be his acceleration? His acceleration would be 9.81, free fall. So if the firefighter was just falling off to the ground, his acceleration would be 9.81. But his acceleration is 4.2. So what happened to the rest of the acceleration? The rest of the acceleration is the part being carried by the pole. So that is the slowing down by the pole. So let's see. It's supposed to be 9.81. Supposed to be 9.81. But it's 4.2 instead. So what do we have to do here? We subtract this from that and find out how much the pole has slowed them down. Because essentially the difference is what the pole is holding. So 9.81 minus 4.2, that gives me 5.61. That's the acceleration that the pole is holding. That's the acceleration that the pole is taking. Knowing that, and knowing the mass of the firefighter, I can work out the force, which is what they want. They don't want the acceleration. They want the force. So I have the acceleration, I have the mass, and I have this formula. Force equals mass times acceleration. Easy. 97 multiplied by 5.61, and that gives me 544 newtons. That's the answer to that one. Okay, so how much is it? 540 newtons. The reason I'm working with 540 is because we have two significant figures over here, two significant figures over here. So I'm keeping it at two significant figures over here. But that's how you do that. Okay? I hope that makes sense. If it doesn't, go back, pause the video, go back, try and understand it. Just remember, if the firefighter was falling, then they would be falling here on Earth. They would be falling at 9.81. So the fact that they are going down at 4.2 instead means that the pole is slowing them down. How much is it slowing them down? Well, it's 9.81 minus the 4.2. Okay, Let's move on. I'm going to take all of this off. If you need to go back to it, it's a video. So that's the beautiful part about videos, is that you couldn't do this in the classroom. You couldn't say, could you go back? I mean, you could, but most of the time, teachers might say, you know what, just wait, or wait after class, or I'll explain it to you later, or maybe you could go and sit next to so and so to explain it to you. Whereas with a video, you can just go back and watch it again. It's perfect. Okay, number 19, and that's a follow-up. What is the firefighter's acceleration of the force exerted on him by the pole is 650? So this time, they didn't give us the acceleration, they gave us the force, which is, in my opinion, easier to work with. We know that the weight force, mass times g, is going to be 950. How do I know that? Well, because we worked it out before. 97 kilograms multiplied by 9.81. So the total weight force downwards is 950. But now the pole is withstanding a force of 650. In the opposite direction, of course. So I've got 950 newtons down, and I've got 650 newtons up from the pole. So now, obviously, the firefighter is still sliding down, but we don't know what the acceleration is, and that's what they want to find out. What is the firefighter's acceleration? Remember to always read the question twice, make sure you understand it fully. So the first thing we need to know is what is the overall net force, because we've got a force downwards of 950 and a force upwards of 650. A force downwards of 950, a force upwards of 650. Overall, the force acting down is going to be, well, that's 300 newtons, isn't it? 950 down, 650 up, so it's going to be 300 newtons in the downward direction. That's the overall force. Because in this system over here, we've got 650 down, 950 up, so the overall force is going to be 300 newtons down. Now that we know the overall force acting down, what can we do? What can we do? Come on. Easy. Easy, that's right. We just use that again. 300 equals 97 multiplied by the acceleration. So the acceleration is going to be 300 divided by 97, approximately 3.1 meters per second squared, downwards, of course. Okay? And that's how you do that. Okay, hopefully it wasn't too tricky. Just make sure you understand net forces. Draw a body diagram if you have to. I always like to draw them because it just helps me visualize things. Okay, I'm going to take this off. Once again, remember it's a video, so you can always go back. So I'm going to take all of this off. Okay. Next we have question 20. What is question 20 asking us? Question 20 is asking us, you lift a stuffed suitcase. Okay, so my students know by now how much I love art. I just love drawing. It's a good skill to have. You know, just kind of a bit like meditating, really. Here we go. It's an old suitcase. Okay, it's an old suitcase. And you know what? I'm going to have Nike on the side. There you go. Made it more modern now. I'm going to go with green. You lift a stuffed suitcase, so the suitcase is not empty. It's a stuffed suitcase, so it's got stuff in it. You lift a stuffed suitcase with a force of 105 newtons. So 105 newtons up, giving it an acceleration of 0.705. So we've got an acceleration that is in the upward direction as well of 0.705. What is it asking for? What is the mass of the suitcase? Ooh, that is a good question. What is the mass of the suitcase? Well, remember, there's acceleration acting downwards, that is gravity, and there's acceleration acting upwards to counter it. Otherwise, the suitcase, let's assume a situation where the suitcase is super heavy and you put in the suitcase on a floor that's not very strong. Then what's going to happen is the suitcase is going to go through the floor because the floor cannot counter the force of weight acting downwards. It's a bit like an elephant standing on a desk. Now, unless the desk is built really strongly, it cannot provide an equal and opposite force. It cannot withstand that, and therefore it will break. So here's what we have. We have a gravitational force acting downwards of 9.81. Apparently, we have a gravitational force acting upwards of 0.705. What that tells me is that there's a force acting upwards to counter this gravitational force, and then some. So what this is saying is that there's a force that counters the 9.81 from gravity, and then on top of that, not only are we countering it, on top of that there's also 0.705 acceleration upwards as excess, extra. Okay? So that's what we need to do. We can't simply go force equals mass times acceleration, because a lot of you will fall into that trap and think, well, hang on, we've got the force, 105, and we've got the acceleration. Well, not really. We don't have the acceleration. This is not the total acceleration. Otherwise, the bag would weigh something like 130 kilos, 140 kilos. This is not the total acceleration. The total acceleration is 9.81 upwards to counter this, the force downwards, plus 0.705. So the acceleration is going to be 0.705 plus 9.81 upwards. And they're both in the same direction. So this is up, so that's fine. Why? Once again, let me explain one more time. There's 9.81 pulling down because we're on Earth, and there's going to be a 9.81 countering that upwards, plus the 0.75 that they've told us about in the question. So the total acceleration is going to be 0.705 plus 9.81. 10.515. Now, I'm not going to start simplifying significant figures or decimal places just yet. I'll do that at the end. Always good practice to do that at the end. The force is 105 newtons. Can I work out mass now? Of course I can. So 105 divided by the answer, 9.99. Now I'm going to keep it at 9.99 because I'm working with three significant figures over here and I'm working with three significant figures over here. What is the weight? Well, that's really easy. Remember, the formula over here is going to be weight equals mass times gravity, which is going to be 9.99, no, we don't need that, 9.99 multiplied by 9.81 here on Earth. 9.81, 98 newtons. I can't write the newtons. There, 98 newtons. That's the weight. That's the answer. 98 newtons. So that's the mass, that's the weight. Okay, I hope that wasn't too hard. Let's move on. Let's talk about springs and spring constants. Now I'm just going to move my face out of the way a bit so you can see that picture over here. Or maybe I should put myself down here. So here we're talking about springs and spring constants, and all this is basically saying if you pull on a spring, it will stretch. So obviously, and not just a string, but any elastic object. So any elastic object will have spring constant. I'm just trying to see if I have an elastic object of sorts. Normally I do. Normally I do, because I've got a whole heap of things over here. So right at this minute, I can't find what I'm looking for. You know what that's called? That's called Murphy's Law. The possibility of something happening that you want to happen, that you don't want to happen, will happen. It's inevitable. Okay. Now I'm not going to spend the whole lesson trying to find a spring. I can't find one, unfortunately, and I can't find a rubber band, but I can't find a tall plane. Not very useful. Okay, let's go. So the force, turns out the force acting on a spring. Remember how we said force equals mass? Oh, let's go back. Force equals mass times acceleration. We know that, and we know that weight, which is a force, is equal to mass times gravitational pull. And then we also have something else now. So we have force acting on a spring equals K multiplied by X, which is the stretch of the spring. Now, what is K? K is this thing called spring constant. Spring constant. Oops, give me a second. Okay. And so, what is K? We know what mass is. That's easy. We know what acceleration is. We know what gravity is. We know what X is. X is the stretch in the spring. So if you take a spring and you stretch it by putting a weight on it, by putting a mass on it, then it stretches, right? And that stretch is called X. That's just a change in position. That's distance. We've seen that in the first 3 units. So that's what that is. And that's the force. What's K? Okay, listen carefully. You've got 2 different springs. You've got a really strong spring and you've got a really weak spring, or a really soft spring. You hang them both up. You put the same weight on both, the same mass on both. Which one's going to stretch more? The soft spring is going to stretch more. So they don't all stretch the same way? No, they don't, and we know that they don't. So if I've got a really strong spring and a really soft one, the soft one is going to stretch a lot more. Why is that? Why? It's due to the spring constant. So you can think of spring constant as stretchiness or strength, if you wanted to, of the spring. And each spring has its own spring constant. And even bands, rubber bands, and ropes and things like that have their own spring constant. And that is a number that tells us how stretchy or how elasticy, how the ability of it to elongate, right? The ability of the spring to stretch. That's what spring constant is. And it's a constant number. It's a constant number. For every spring, there is that number. So once you know that, and once you know the stretch, then you can work out the force. So an example is, let's say, for example, I have a spring, and this spring, I put a 1 kilogram mass on it, which is 10 newtons, just for ease of calculations. Now that spring has stretched by 10 centimeters. I'm going to make it really easy, 10 centimeters. Work out the force. So the force is going to be Kx. I don't know K. Sorry, not the force. Work out the spring constant. So I know the force. The force is 10 newtons. K is what I'm trying to work out. And then the x is the length, which is 10 centimeters. So it's stretched by 10 centimeters. But of course, we know that length in physics is in meters. So I've got to change 10 centimeters into meters. And how many centimeters are in a meter? Please don't tell me you don't know this. Here's a meter ruler, and it has how many centimeters in it? I'll bring it closer to the camera. It has 100. Can you see it? 100 centimeters. So 10 centimeters is equivalent to 0.1 meters. How do I know that? 10 divided by 100. So now what? Now what do I do? Well, now what do I do? It's 10 divided by 0.1, and then I can work out the spring constant. So 10 divided by 0.1, and that equals K. Therefore, K equals 100. What is the unit for K? What's the unit for K? How do I work out the unit for K? I'm going back up there. What's the unit for K? Well, let's see. The unit for force is newtons. The unit for K, we don't know. I do know, but I'm just going to show you how to get it. And the unit for length, or x, is meters. So I must multiply this by that in order to get this. How about newtons over meters? What does that do? If I multiply newtons over meters by meters, then these two cancel out, and I'm left with newtons, which works out. So the unit for K is newtons per meter, which makes sense. Okay, and here we've got some examples. So a spring with a spring constant of 21 newtons per meter. Remember, we just found that unit before, and here it is. So that's K. I'm not going to do that. You know what I'm going to do? I'm going to do that. K equals 21. It's stretched by 3.4 centimeters. So X equals 0.034. What is the force required to cause the amount of stretch? Come on, guys. Really easy stuff. So the force is going to be, you don't even have to change anything. You don't even have to move things over to the other side. It's 0.034 multiplied by 21, which is about 0.7. 0.34 multiplied by 21, which is 0.71. We're working with two significant figures. So let's keep it at that. And we have worked out the newtons, haven't we? We have worked out the force. Okay, let's look at question 21. See what they want. Question 21. Pulling on a spring with a force of 1.2 newtons causes a stretch of 6.4 centimeters. What is the spring constant of the spring? Pulling on a spring with a force of 1.2 newtons. So the force equals 1.2 newtons. The stretch equals 0.064 centimeters. No, meters, afwan. What is the spring constant? The spring constant is going to be F over X equals K. How do I know that? Well, there's another triangle for you. Excuse me. Okay. So here we go. So we've got F, which is 1.2, and we've got K, which is 0.064, and that's going to equal, come on guys, you can work this out yourselves, and hopefully some of you have, 18.75, 19, because it's two significant figures. So 19 newtons per meter, because we're looking for the spring constant. I'm going to change the colors. I'm getting bored with this one. That one. Let's go to question 22. Question 22 says, what is the stretch when you pull with a force of 2.3 newtons on a spring with a spring constant of 19 newtons per meter? So we're looking for X. So how do we find X? It's going to be force over K. I'm just going to write the formula all out again because I know some students of mine want to see it. I'm talking to you. You know who you are. There's always that one student who's like, where did you get that from? So I always like to show all my work out. That's what I'm supposed to do as a teacher. Okay, so what is the stretch? That's how you work it out. That's step one, step two. Step three is going to be actually putting in the numbers, which is 2.3 divided by 19. Mm-hmm. 0.12 meters. So how much did the spring stretch? That much, or 12 centimeters. Not bad. 12 centimeters is quite a stretch. This much. Moving on. Strings transmit forces from one place to another. I'm not going to spend a lot of time on this. All you need to know here is that basically you can use rope or you can use string to transfer forces from one place to another. Obviously, think of a cart that's being pulled by a cow, or think of a car that's stuck and then somebody pulling the car out, or think of a trolley being pulled with a rope of sorts. So you can actually transfer forces using ropes and strings and things like that, which is very convenient because we've been using them for centuries. And a classic example would be a water wheel, where you pull the water out using a bucket, and obviously using pulleys and using a rope. So you can transfer forces using ropes. The force on a rope or a string is called tension. So tension is the force exerted by a string, rope, or wire being pulled. Easy. Even if you had long hair, so if you had long hair like a braid, I guess girls do, um, that can actually transmit, um, transfer tension through it. Yeah. And of course, if the object is not moving, so it's not accelerating, it's not changing its direction, and it's not speeding up or slowing down, then there's no net force acting on it. If an object's traveling at constant speed, there's no net force acting on it. If it's not, so since it's not slowing down or speeding up, and if it's not changing directions, then there's no net force acting on it. And that's the same case. If you tie an object, if you pull on something and you tie it down, then the tension in the spring is in equilibrium because it's not moving. Let's look at an example, and examples make everything easier. So a person hoists a bucket of water from a well and holds the rope, keeping the bucket at rest, as in case 1 below. A time later, the person ties the rope to the bucket's handle so that the rope holds the bucket in place, as in case 2. Is the tension in the rope in case 2 greater than, less than, or equal to the tension in the rope in case 1? Bit of a mouthful, that. So you really need to understand the question before you start proceeding with the answer. The pictures help. We've got a person pulling on the bucket, and obviously all the tension is going through one rope. And here we've got the person who's tied the bucket, and now the tension is across 2 ropes. And what it's asking is it going to be the same? Are these 2 equal, or is the tension in one greater than the other? Okay, I want you to think about the forces involved. The bucket, what's the force involved with the bucket? It's got water in it. It's heavy. It's mg, weight. Weight equals mass times weight equals mass times gravity. So that's the force acting down. The force acting up, what's countering that force is tension. Tension on one rope. And here the tension, the same tension, mg is the same. It's the same weight. The same weight. Except here it's on one rope, and over here in the second case, we've got mg, and then we've got equal and opposite force, Newton's third law, but this time it's counted by two ropes. So is the tension double? No, it's half. It's half. So essentially, that weight force is being carried by two ropes, and therefore each rope is carrying half. Here's a really fun experiment I want you to do. I want you to stand up, and I want you to stand up on your two legs. So stand up just the way you do. Stand up on two legs, on your 2 feet. And what's happening is your weight is being carried by your two legs. Now, as soon as you lift one of your legs, so just stand on one leg, and you'll feel the difference immediately. That one leg is now carrying your entire force, your entire weight. So it's double. Suddenly your leg is carrying double the weight. The same thing happens here with the ropes. When you have two ropes, they're carrying half the tension force. The total force is the same, but now it's across two ropes. Common sense. That's why I like physics. It's just common sense. So what's the answer going to be? The answer is going to be, in case 2, the tension in the rope is going to be less than. How much less than? It's going to be half. Half the tension of case 1. What if we have 4 ropes? What if we have 4 instead of 2? What's it going to be then? It's going to be a quarter. Is it? Yes, a quarter. Because each rope will carry a quarter, the same total, but then each rope will carry a quarter of the tension. Let's look at this example here. Oh boy. Okay. I read it once internally and then I read it again. And that's how I always read a question twice. A 1.84 kilogram bag of clothespins hangs in the middle of a clothesline, causing it to sag by an angle of 3.5 degrees. Find the tension force, capital T, in each part of the clothesline. Okay, easy, easy. What do we do? Remember, always start with the forces with a free body diagram. What is the force? What are the forces involved here? We've got a clothespin bag. So here's the bag. And as you are used to me by now, I'm always going to try and draw some pictures to make it easy. So clothespins, I'm going to make a transparent bag. You know what clothespins are, don't you? This is a clothespin. Oh, I'm going to try and attempt to draw one from memory. Why not? Why not? Let's see how good my memory is. Oh, that's not bad. I'm sure I didn't get 100%, but that's what a clothespin is. Okay, they hold clothes in place. Okay, so that's kind of what it looks like. You clip clothes with it. So this, we have a bag, and the bag is sagging. We're going to take that off now. The bag is sagging, but it's being held by two poles. Let me draw the poles a bit more straight. So the first thing that's quite obvious is that there's a weight force pulling down, mg. What's that weight force? Do we have m? Yes, we do. Yay, they're being very generous. So we've got 1.84 kilograms. We've got g because it's Earth and 9.81 meters per second squared acting downwards. Acting downwards. So then what's the story? Alternatively, by the way, you could write newtons per kilogram. Both of them are acceptable. So what's going to happen? I want you to think about this one for a while before you start your attempt to answer it. Pause the video if you have to. I'm going to answer it now, but please pause the video. Give it a try. Here's a clue. Remember that the force upwards to counter the force of weight is going to be divided across two ropes. Okay, so this one is going to carry half the force, this one is going to carry half the force. But you're going to have to work out the vertical and the horizontal components. Okay? And now I'm going to solve it. So here's the deal. I've got to work out, I know that mg acting downwards is that, so I need to work out what the weight force is, and the weight force is going to be 1.84 m times g, which is 1.84 times 9.81, 1.84 times 9.81, and that's going to be 18 newtons down, or 18.0504. So now that, I know it's going to be 18 newtons up, so I know the tension on the spring, total tension is going to be 18 newtons up, but that's not what the question is asking me. It's asking me to find the tension in the spring in each one of those ropes. Now you might be tempted to say, okay, 18 divided by 2. That's not how it works. You see, it's 18 up, up, and this is not up, this is to the side. Does it make a difference? Of course it does. Of course it does. How so? I'll tell you. I want you to imagine that scenario. Here it is. I want you to imagine a really heavy object. A really heavy object. I have one here. So I have a hammer, which is a heavy object. Now it's quite easy holding the hammer like that. But then as I stretch out the spring and I'm trying to hold it straight, that's harder. That's easy. That's harder. So the forces are not the same. If you try, if you had the ropes acting this way, so if the bag was like that, and then you had the ropes like that, then it'd be easy. Then it'd be 18 up, but that's not what's happening here. The 18 up is divided across two, but it's only the y component of both axes. So what we have is we have a triangle, and we have a force acting this way and a force acting this way. And likewise, we have a force acting this way and a force acting this way. That's what we have. So just to be more accurate, I'm going to get rid of the two poles, and I'm going to keep the rope, but I'm going to also draw the other parts of this triangle. So the 18 acting upwards to counter the weight is going to be the y component. So that's 9 over here and 9 over here. But of course we have, now I just want you to imagine that these two sides are the same. So what I'm being asked to do is work out the tension force here and the tension force here. But I don't have the adjacent force. I don't need that. I don't need that. Why? Because I have the angle. They've been nice. They've really been nice. So 3.5 degrees here. 3.5 degrees here. Easy peasy now. So, Sokatawa, guys, come on. Sokatawa. Okay, so the tension is going to be, that's the opposite. I'm trying to work out the hypotenuse, so I'm going to use sine. Sine theta equals 9, no, not 9, opposite over hypotenuse, which is 9 over the force. That's what I'm trying to find out. I'm going to take this away. I'm going to draw a bit of space here for me. So basically, sine 3.5 equals 9 over this. So what's it going to be? Sine 3.5. 9 divided by sine 3.5. And that gives me 147 newtons. That is the answer. Easy. Hopefully that wasn't too hard. It did require a bit of thinking, but it wasn't too hard, was it? Let's move on. Okay, great. Lesson check. Let's start with the concepts. We've got list all the steps that are followed when using a free body diagram or when drawing one. When using a free body diagram. Okay. So I would say for the steps, oops. Oh, that's the last slide. Yay. Okay. For the steps, I would say draw the vectors. Okay. So the first step would be drawing the vectors. And the components. So both x and y. X and y. Sorry about my chicken handwriting. So here's an example, like x vector, y component of this vector here. So let's say that's the vector 6 newtons, and then I can work out the x and y components. And then the third would be to apply F equals ma, Newton's second law. 24. What equation is used to determine the weight of an object with mass m? I love these easy ones. F equals mass times acceleration, which is the same as weight equals mg. I think that's what they're looking for. 25. If an object is at rest, what can you say about the forces acting on it? The net force is 0. The forces are in equilibrium. They are in equilibrium. That means they're all like equal and settled. 26. State Hooke's law describes the connection between the stretch of a spring and the force it exerts. What is the connection? The force acting on the spring is equal to spring constant multiplied by the stretch, and that is in meters. 27. To increase the angle of a sag in active example 5.10, is it necessary to increase or decrease the tension on the clotheslines? Explain. 5.1. What did they want to do? Increase or decrease the angle of sag. Decrease the angle. Oh, yeah. And what are they asking for? Is it necessary to increase or decrease the tension? Now, let me go back to my example then. My example with the hammer. Decrease the angle. So they want me to decrease the angle. What am I doing to the tension? It's increasing the tension. This is decreasing the tension. This is increasing the tension. So in order to decrease the sag or decrease the angle, I have to increase the tension. Increase the tension. Increase the tension. Um, um, the reason why that is, the output component can be provided by a force that is inclined at a small angle, as long as the magnitude of the force is very large. Okay, so that's why that is. 28. I don't have any space. So what I'm going to do is I'm going to go back here. Bear with me as I take all of this off. I can do some waiting songs. Do, 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 do. Do, 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 do. Do, 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 do. Do, 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 do. Diagram. A 9.3 kilogram child sits in a 3.7 kilogram chair. Her feet do not touch the floor. Here we go. That is the wee lady. And there we go. She's sitting on the floor. Her feet are not touching the floor or the ground. Draw a free body diagram of the child and find the normal force exerted by the chair on the child. Okay. Me. We've got mg acting down or weight. And we've got the normal force acting upwards on the child. That's what it looks like. Find the normal force exerted by the chair on the child, by the chair on the child, by the chair on the child. Not by, they don't care about the floor or the ground. They want the chair on the child. So we're going to assume this is, the chair can be assumed to be like the floor because the chair is carrying the full weight of the child. So that's easy enough. It's going to be, A is going to be 9.3 multiplied by 9.81 because that's how much force the girl is exerting down on the chair, her weight. So her mass multiplied by the pull of gravity, that's how much force she's exerting down. So the chair has to withstand that. The chair has to hold that, which is 91 newtons up. That's how much the chair is applying. B, draw a free body diagram for the chair, and find the normal force exerted by the floor on the chair. Well, it's exactly the same. And they want to know now what is the force being applied by the floor on the chair. Remember, the chair is also carrying the child. So it's going to be still the same, F equals mg, except this time m is going to be 9.3 plus 3.7 multiplied by 9.81, and that's going to give me some number. About 120. 9.3 plus 3.7 plus 9.81, and that is 128 newtons. Okay. If I'm being pedantic, 130 newtons because we're working with two significant figures. Number 29. Number 29. Here we go. Wasn't sure if it's working there for a second. I think I'll stop at number 29. A spring with a spring constant of 62 stretched 19 centimeters by an applied force. What is the magnitude of the force? Easy. Force equals spring constant multiplied by x, which is the stretch. As we already said, that would preferably be in meters. 62, the spring constant, multiplied by 0.19, which equals, of course, the unit is newtons. About 12. 0.19 multiplied by 62, and it's about 12. 30. I don't think I'll do 30, but I'll read through it. Two astronauts push on a satellite. One pushes in a positive x direction, 42 newtons. The other pushes in the positive y direction, and they don't tell you how much. Some newtons. We'll call it x newtons. Oh no, I don't want to call it x newtons because people will be confused. Y newtons. If the net force is at an angle of 15 degrees above the x-axis, what is the magnitude of the second astronaut's force? Easy. Soka toa for that one. So ka toa. They're looking for this. They've given us the angle. That's opposite over adjacent. So I'm going to use tan. Tan 15 equals yn, opposite over 42. Yn is equal to tan 15 multiplied by 42. 11 newtons. Okay, that is that. That's it. Now, if I go ahead, so that's 11 newtons on this side. That's the answer. 11 newtons. What's the overall force from both astronauts? That's going to be 11 squared plus 42 squared and the square root of that, which is 43 newtons. Okay. And with that, we've come to the end of the lesson. I'm sorry today's was a bit long, but I hope you understood it. All the best. Ciao. See you later.